Welcome to the third of our three-part installment on sensor errors and calibration. In this lesson, we'll explore various sensor errors. There are a number of types of errors that can affect your measurements for a mechatronic system, and the first one we'll look at here is the linearity error. If you recall, when we were calibrating our sensors, we tended to apply a linear fit to our calibration data, such that y, our output, was equal to a0 plus a1 times x, where a0 was the y-intercept and a1 was the slope. So for calibration data such as the data here, where x is my input and y is my output, this linear calibration curve might look something like this. The problem here is that there may be some curvature, let's say, to the model of the sensor, and what I've drawn in blue here might be the actual function describing the sensor performance. So the linear fit in red is really an approximation. And because of that approximation, we're going to have some linearity error. So this linearity error, we're going to call that E-linearity. That's going to be a function of whatever input I have, and that's going to be equal to y linear minus the true value y of x. And this error, that'll have the same units as my output. So whatever the units of y of x are, I'll have the same units for my error. Now, one thing we tend to do with error is to frame the error of a sensor in the same context. So we'll frame this error within the output range of my sensor. So let's define this range then. We'll call this the output range R0, and then we'll look for the maximum linearity error. So that'll be here. So this distance right here, we're going to refer to that as the error or E-linearity max. This allows me to define a percent linearity error that'll be equal to the error linearity max, so this distance here, divided by the output range, R0, all times 100. And this is often provided as a percent full-scale output range, so you might see this in a datasheet. Another phenomena that you'll often see with various sensors is that if I provide an input to my sensor, so say X, and let's say the input looks something like this, so it's gradually getting a larger output, y of x, as I increase my input. Yet when I decrease x, I sometimes will get a different curve as my y of x values decrease back to the original position. So now the return phase is looking different than the loading phase. And this is what we refer to as hysteresis in our sensor. And hysteresis really comes down to memory. By memory, we mean that the performance of the sensor is dependent if I'm increasing my load or decreasing my load. The problem with hysteresis is that for a given input, so let's call that x here, I could have two potential different output values, right, based on what the previous value was. So in this sense, I could be here and move up a little bit, landing at this value of y of x for the same x, or I could be here and move down a little bit, arriving at a different y of x for the same input x. So we have two different outputs, and I'll call those y low, yl for short, and y high, or yh for short. And they're both based on the same x input. So this then is my hysteresis error. We can also define a percent hysteresis error, and this will be related to the full-scale output range. So my percent hysteresis error will be equal to yh minus myl, so this hysteresis error here, divided by the output range, R0, all times 100. Another type of error that is commonly found on datasheets is the sensitivity error. So we might have some typical sensitivity in our sensor, and we'll call that k-tip for typical. And I might have some bounds on that. So I might have some lower bound where I have a minimum sensitivity and an upper bound where I have a maximum sensitivity. One way to quantify this sensitivity error, in addition to using the output range from before, is to use this input range. So R sub I would be my input range and R0 would be my output range. In this case, my sensitivity error will be defined as Kmax minus Kmin, which would have units of output over input. We'll multiply that by Ri divided by R0 times 100. Now, there are several different types of errors that will prop up into your measurements. We've gone over 3 now. And if we want to get an understanding of the overall quality of the data from our measurements, then we want to take a look at the total error. For the total error, we're going to look at the root mean square. So we'll look at the square root of the sum of all of those errors squared. Of course, the requirement here to use this equation is that all of these errors have the same units. As a quick example, consider the case where we have a maximum linearity error of 2% and a hysteresis error on the order of 1%. The total error then would be the square root of 0.02 squared plus 0.01 squared, which will be equal to 2.2%. So this total error, this will give me some idea of the spread of data that I might expect during my measurements, and some idea of the total accuracy of my measurements.